Welcome to UV Physics Academy. So here we are discussing quantum algorithms. In this seventh part, I am going to discuss about Simon's algorithm. So what is this Simon algorithm? So let us suppose here we have a function f of x which is 2 to 1 function. What is the meaning of this? It maps two inputs for every one output. That means two different inputs are having same output. Let me explain more clearly. So for example, here you have x and this is f of x output. Now let us suppose somewhere here we have an input x1 and x2 after some periodicity, let us suppose x2. So then this is f of x1 and this is also this is f of x2. According to this algorithm, if f of x1 equal to f of x2, that means the outputs are same for the inputs x1 and x2. This is possible only when this x2 equal to x1 XR yes. Okay, so that means here this S is some hidden periodicity. So for example, you have taken another two inputs where x3 and x4, let us suppose. If those two are also having same output, then that x3 and x4 are related with this hidden periodicity. Either x4 is equal to x3 xrs or x3 is equal to x4 xrs, whatever it is, both are the same. And this addition is nothing but the bitwise binary addition. Okay, so now I hope you understand what is this algorithm. Here we have a function which is having some hidden periodicity. Okay, so our aim is to find that hidden periodicity. If you have two inputs x1 and x2, if they are having a same output, this is possible only when that x2 and x1 are differ by some periodicity, that is x2 equal to x1 xr s. So we would like to find that periodicity s. Okay, so now let me explain what is this what is meant by this bitwise binary addition. So bitwise binary addition, let me explain what is this. So for example, if you have x1 x2 x3 xr y1 y2 y3, so here you have to add bitwise. That means if you take x1, you have to take y1. You should not add y2. That is called bitwise. So here x1 plus y1, x2 plus y2, x3 plus y3. Okay. And x1 plus y1, here again you have to take modulo 2 operation separately, and here also modulo 2 operation, and this is mod 2 operation. Let us take example. Now if you take example, here first I am taking a binary notation. So what I found is we can do this algebra by using a decimal notation also. Okay, let me explain first binary notation. So here we have, let us suppose 110 XR 101, let us suppose. Then you have to add bitwise, remember. Okay, so here 1, here 1. So this 1 plus 1 2, if you take modulo 2, that is a 0. Next 1 plus 0, it is 1 only. Next 0 plus 1, that is 1 only. Clear? Take one more. So here we have one more example. So let us suppose we have 111, something like this, XR and 101. This is nothing but first you have to take this 1 that is 1 plus 1 2, you will get 0. Next 1 plus 0 that is 1, and next again 1 plus 1, that is a 0. Now let me take a decimal state notation. This is quite interesting. So I hope you understand what is this XOR operation. Maybe just I'm just comparing, trying to compare. Okay, so in this decimal state notation, it's quite interesting. Please see. Now I'm taking the same first example again. This is in the decimal state notation. First one is a 6 XOR, and the next one is a 5. How to do this? Remember, this is a 3 qubits. So what is 6? Actually 3 qubits are there. That means like this, 1, 2, 4. How to get 6? That is a 4 plus 2 plus 0 XOR 5. 5 is nothing but 4 plus 0 plus 1. So what I want to say is, just find the common numbers. What are common numbers there? 4, 4. Here 4, there 4. Just cancel those common. Cancel the common numbers and add the remaining numbers. It's just general addition. Just a general addition. That is a 2 plus 0 plus 1, 3. Now convert into binary. That is 0, 1, 1. Same answer. Now let us try one more. Now here second one I am taking. So no doubt this is nothing but 7, 3 qubits XOR 5, 3 qubits. Right? So in this case, this is nothing but 7. How to write 7? 4 plus 2 plus 1 XOR 5. 4 plus 0 plus 1. So what I said, cancel the common numbers. 4 common, cancel in both. Next 1 common, cancel in both. Then we will get 2. So exactly this is also 2. You can convert into binary later. Just do the algebra, after that convert into binary. Okay, so anything you can do. Just what I feel is I found some decimal state notation addition or something like that. So I think that's why in XOR gate, generally go back to digital, in XOR gate we will call it as inequality finder. So that's why what I feel is, if you have the common numbers, just cancel that, and you will get this just after that, after cancelling the common numbers, is just a small general addition only. Let us take a little bit big number. So for example, if you take some big numbers, let me take I'm taking this 10 4 qubits plus 15, so 4 qubits time. So let us take here, what is this 10? The 10 stands for 8 plus 0 plus 2 plus 0, 8 plus 2, 10, XOR 15, all on, that's why 8 plus 4 plus 2 plus 1. Now I request you please cancel that common. 8 common, so 2 cancel. What's the remaining? 4 plus 1, 5. It's not 4, it's a 5. Now let us check by using that binary addition whether we are getting the same answer or not. This is a 10, 1, 0, 1, 0, and this is a 15, all ones. If you add, this is a 1, here it is 2, if you take modulo 2, it is a 0, and this is a 1, and here it is a 0, which is nothing but 5. Of course, here 4 qubits. Okay, now, so that's it. This is the bitwise binary addition. Now let us proceed how to get the tabular form, that x f of x. Right. Now here once again, please go back to the algorithm, that is f of x1 equal to f of x2 such that x2 equal to x1 XOR s. This s is the hidden variable, hidden periodicity or whatever it is. Okay, now let me take one example. Let us suppose s equal to 3, that is 1, 1. In decimal we can write it as a 3. How we will get that a tabular form? So here we have table So this is x, and here we have, sorry, here we have x, and this is f of x, right. Now you can take here, okay, so let us start. Now for example, if you take 0 xr, what is the variable? 3. So let us take algorithm again. So here I am going to explain how we are getting that tabular form, that input and output. So once again go to this algorithm. Here we have f of x1 equal to f of x2 if this is possible only when x2 equal to x1 xr's s, where s is some hidden periodicity. That's it. Okay, so now let us take some example. First one, I am assuming s is equal to 1 1. In decimal we can write it as a 3. How to construct the tabular form? This is quite interesting. Now here I have 0 xr 3. Here completely I am following that decimal only because I am comfortable with this. 0 3, there is no common, that's why 3. And if I take 1 xr 3, 1 we have 1, but 3 contains 2 plus 1, 1 is a common, cancel, and you get 2. This, what is the meaning of this? See, if you carefully see, x2 and x1 are having same output only when this condition is satisfied. Okay, so that means I have x1, I added this s, then I got x2. So then x1 and x2 are having same output. So here 0 and 3 have same output and 1 and 2 have same output. Then your tabular form, this is x and this is f of x. If you take, so this is a 0, 1, 2, 3. And from this addition we can say 0 and 3 have same output. Let it be a. Some I have seen many places, so some people are bothering about that output. Here you need not to bother about that output. Let it be some a. Of course a belongs to what again? 0, 1, 2, 3 only, because the 2 qubits you have taken. It may be 0, it may be 1, it may be 2, it may be 3. And this 1 and 2 have same output, and let it be some b. Remember, no need to bother about this AB. This AB belongs to again 0 to 3, but a distinct, that is most important. A never be equal to B. Okay, let us take one more. Now if I take S is equal to 2, that means 1 0. In decimal we can write it as a 2. Okay, so I will take here. Right, so I have written here AB belongs to Z 0, 1, 2, 3, anyone. But remember A is not equal to B. No need to bother about these outputs. Okay, right. So it may be some value which belongs to either 0 or 1, 2 or 3. Next, if I take second example, S is equal to, I am taking 1 0, let it be 2. So 2 qubits. Now careful. So 0 XR 2, which is equal to 2. No problem. 1 XR 3, sorry, XR 2. So there is no common. So 1 and 2 no common, that's why it is 3. It's very clear. 0 and 2 have same output. 1 and 3 have same output. So here x, here f of x. Now this is 0, 1, 2, 3. Now it's very clear. 0 and 2 have same output, let it be A. I told you no need to bother about that. And 1 and 3 have same output, so that is B. In this, the more important thing is not that output that output AB. Only the thing is here we have to find that hidden periodicity S. Okay, let us take a 3 qubits example, how to construct the tabular form. So I'm taking the third example, S is equal to 110, that is a 6, right? Now let us start. Here it is a 0 XOR 6, we can write it as a 6 because there is no common, and a 1 XOR 6, here also no common because the 6 is what? 4 plus 2, that is a 1. So that's why there is no common, that's why it is a 7. I hope now you understand. 0 and 6 have same output and 1 and 7 have same output. Let me take the table here itself. X f of x, this is a 0, 1, 2, 3, 4, 5, 6, 7. Right. Now it's very clear, 0 and 6 have, 0 and 6. Same output. I am assuming it as usual. I am assuming it as A. I told you no need to bother about that A, just leave it. Next one, we have 1, 1 and 7. So this 1 and 7 have same output, that is B. Next one, I am taking a 2 XOR 6. Here common is 2. That's why 2 cancel, 4 remains. Now tell me what are having same output? 2 and 4. 2 and 4. So let it be C. And the remaining 3 and 5. Let us check that also. 3 XOR 6. Now 6 is having 4 plus 2, 3 is having 2 plus 1, 2 gets cancelled, then 3 plus, 4 plus 1, 5. Still not understanding. This 3 is nothing but 2 plus 1, of course 3 qubits plus 0 here. This 6 is nothing but 4 plus 2 plus 0. What shall I cancel here? 2 cancel. Then 4 plus 1, 5. Right. Then this 3 and 5 have same output. So no need to worry about this A, B, C, D. Some values, some value. Okay. So here this A comma B comma C comma D belongs to this 0 to 7. I am using a decimal state notation because it's easy to write, otherwise we have to write many bits. Okay, so that's it. But remember, all are distinct. So no need to worry that A may be 7, B may be 6, C may be 4, D may be 3, something like that. Okay. So I request you please try this one. The next one I'm giving for you, that is S is equal to 101, please take, and let it be, this is a 5. Okay. So 3 qubits. I request you please try this. Okay, right. So how to add this XOR addition, that is a bitwise binary addition modulo 2 operation. Just take a decimal state notation and cancel the common numbers and then general addition. Cancel the common numbers and general addition. It works. Please believe me, it works. Right. So this is about tabular form, and now let us go to the circuit, quantum circuit. Right. So here we are going to take the quantum circuit corresponding to this Simon algorithm to find this hidden variable S. Okay, right. So let me take, right. So here we have this input 0. Here I am representing this we have n number of that parallel inputs, 0 states, and on that we have this head mod operations. So h tensor n, and here also we have n number of inputs, parallel inputs. Let me represent like this. And if you come to this side, right side, here we have measurement. Okay, so this is here also this n number of qubits, and here we have measurement, and after that here also n number of qubits, and after that the same thing, h head mod operation like this. Okay, fine. So this is the quantum circuit. Okay, and what about this oracle UF? So this oracle function is UF. So for example, if you have x of n number of qubits and this is a 0, so this one is a 0, and here after head mod operation you may get a linear superposition actually. So that's why I have taken x, it may be anything. So under this UF, this will become xn, and here once you measure here, this is a second register, so you will get f of x. Okay, that output. Okay, so but remember, any two of the two arbitrary inputs, okay, having the same output, but that two arbitrary inputs are related with this periodicity s, that is the most important. Okay, fine. Now let us proceed to solve this circuit. Now here we have h tensor n operates on this 0 n, and again here nothing is there means identity. Again here also we have 0 n. This is nothing but 1 over root n, 1 over root n. The first one creates a superposition, that is a summation x. I hope you know this. X is equal to 0 to n minus 1. And after that this is nothing, it's leave it as it is, that is 0. Now I'm taking this oracle function, let it be UF. So under this UF operation, I hope already explained here. So this is nothing but 1 over root n summation x, where x is equal to 0 to n minus 1, and here it is a f of x. Remember, all are n number of qubits, n qubit string, something like that. Okay, so now here, this is very important. Now go back to the tabular form. Earlier we have already discussed. So remember, so two arbitrary inputs are having same output, but those two inputs are having that relation, this relation, x2 equal to x1 xr s. That is what we have to find, that s. Okay, here I am taking that tabular form x f of x. Careful. Somewhere, let us suppose we have some input z, and somewhere else we have z xr s. Okay, and this z is having output f of z, and this z xr s is also having output f of z. So these two inputs are having same output. I told you no need to bother about that output, just some f of z. Okay, so now I'm going to write this as summation. If I expand this, somewhere I will get this term. Somewhere I will get this corresponding to the output f of z. So I'm focusing on that. Okay, so let me take. So here again I'm going to expand this 1 over root n, some term, some combination of any two inputs, some other combination of two inputs, plus, now I'm taking this z plus z xr s. Okay, wait a minute, no need to get tension. So these two are having the same output, that is f of z, plus some other combination, plus some other combination like this. Now I would like to write here root 2. That's why this will become, I think we can write it as n by 2. That's not a problem. Okay, fine. Now remember, this is your second resistor and this one is at first resistor. I hope everybody understand this. Okay, so this we have written from that tabular form. So somewhere two arbitrary inputs are having Z and Z XR S are having same output. So I have taken that. Fine. Now let us suppose second resistor is measured. Second resistor is measured. Now here. So once the second resistor is measured, what I will find? Let us suppose it is f of Z. Okay, the second resistor is nothing but f of Z. Then definitely our first resistor is collapsed to this one. Like this, many outputs will be there. Some other f of Z1, some other f of Z2, something. Okay, anything you can take. You may get one doubt. So shall I take another combination? Yes, any combination will give you the same answer. No doubt. So then definitely this first resistor is collapsed to this Z plus ZXRS over root 2. Next I have to consider this head mod operation on the first resistor. Remember, so this is the first resistor and this is the second resistor. Cool. Now let us apply the head mod operation on this first resistor. Now I am taking head mod operation first resistor. So this is nothing but H tensor n. Here we have first resistor Z plus Z XR S over root 2. You know already that parallelism, quantum parallelisms class I have already explained. So this H tensor n, because these are n qubit strings, okay, n number of head mod gates are operating on that, then you will get 1 over root 2, just I am writing outside, and here you will get 1 over root n again, because n number of qubits are there, capital N is equal to 2 power n. So if H tensor n operates on Z, maybe if you forget, I will write here the formula. H tensor n operates on Z, we can write it as summation. I am taking it as a y here. That's why y equal to 0 to n minus 1 and a phase factor minus 1 whole power y dot z. I have already explained that y dot z, binary dot product, okay, bitwise binary dot product. Of course, normalization constant, that is a 1 over root n. So let me write here. So this is the summation minus 1 whole power. First one is a z, that's why y dot z into y, of course n qubits. This y equal to 0 to n minus 1 plus again summation minus 1 whole power, this time y dot z xrs, and here again y, and here also y is equal to 0 to n minus 1. Clear? Right. Now let us take out some common. So don't bother about this, just leave it. And here we have 1 over under root 2n summation y equal to 0 to n minus 1 common, and after that see carefully, this minus 1 whole power y dot z plus minus 1 whole power y dot z XR S, okay, and outside I have taken this Y. Now please concentrate on this. What is this? This is Y dot Z XR S. This can be written as Y dot Z plus Y dot S. Of course, XR operation will be there, but here we are separating it. Okay, so then this can be written as minus 1. Here I am taking common. Minus 1 whole power Y dot Z also I am taking common. Then it will be 1 plus, already minus 1 whole power Y dot Z gone. That's why minus 1 whole power Y dot S. This Yn is as it is, and summation over Y equal to 0 to n minus 1, 1 over root 2n as it is. Okay, now carefully see that middle term. Now here you are talking about this entire thing, you are talking about what is this? This is the amplitude of Y. Okay, so now here we are having one property. So for example, please focus on this Y dot S. For example, if I take Y dot S equal to 0, if I take Y dot S is equal to, or Y dot S is equal to 1. If Y dot S equal to 1, minus 1 whole power 1 minus 1, but here it is 1, okay, and this entire thing will be 0. So finally we can say this amplitude of Yn means that n qubit string is a 0. So if I take Y dot S is equal to 0, then definitely amplitude of this Y is not equal to 0. So this equation, okay, that equation is giving you a system of linear equations. This Y dot S equal to 0, this gives system of linearly independent equations to solve yes. If you solve that system of linearly independent equations, we will get that S. Okay, so here we have it depends upon the number of independent equations, depends upon the number of qubits, okay, of course. So that's it, and while we will explain this algorithm by using some example, then you will understand what is that a system of linearly independent equations. So once again, please check what we have done here. So this is the Simon algorithm, and the main statement is this one. That means f of x1 equal to f of x2. That means the outputs of two distinct inputs are same. This is possible only when that two inputs are having a relation, that is x2 equal to x1 XR S, where S is the hidden periodicity. That is what we are going to find. Okay, so and this is the most important thing, so carefully observe, and if you have any doubt, so I request you please inform. That's it, and example is quite interesting, so you will understand more clearly whenever we are discussing the example. So let us discuss the example.